on Earth is dependent on energy. The sun, our energy source, which has been warming our world from the very beginning. Plants, animals, and humans all depend on this life-giving light and heat. But then something happens. Man discovered other sources of energy. First by utilizing fire, then coal, oil, gas, and atomic energy. But our insatiable hunger for energy has thrown our environment out of balance, a disruption that now threatens life on Earth. We need to find new, cleaner energy sources. Right now, all over Sweden, research is underway that may solve our planet's great challenge. This research is about specially designed molecules, completely unique nanomaterials, recreating photosynthesis, and new smart solar cells. The obvious first choice in the hunt for energy is to look to our original source, the sun itself.
Yeah, this is a very nice house where the whole facade is covered with solar cells.
Charlotte Platzer-Björkman wants to utilize our sun's energy with her solar cells. But these aren't your usual solar cells, which tend to be large and cumbersome.
So this is something called thin film solar cells, and that's the second generation as opposed to silicon solar cells, which is the first generation. And thin film is what I do my research on.
Thin film solar cells are only 1/100th the thickness of ordinary ones. This opens up a whole new arena for their use. The drawback is that these solar cells are made of rare metals, which in the future there will not be enough supply of. At the Skogström laboratory at Uppsala University, Charlotte's team is developing a new type of thin film solar cell.
Here we have some of our new solar cells, and they look like the other type.
But inside the cell, there are big differences. She's using completely different metals.
But the difference is that these only contain zinc, copper, tin, and sulfur. They are very abundant elements and thereby cheaper.
Charlotte's team has come a long way with their new solar cell, but its efficiency is still quite low.
Today we're not taking care of the blue part of the spectrum in a very efficient way, and that's what we want to try to do now.
When the sunlight hits a solar cell, electrons are released. They move up into a material and then through a cord to the backside, and in doing so, they create electric current. How much power can be generated depends on how well you can take advantage of the energy of light. Thus far, researchers have been working to make effective use of visible yellow light. But now, Platzer-Björkman's team is working to make effective use of the invisible blue light as well. To do this, Charlotte's team has to develop another type of solar cells, called top cells. And they do that here, inside the dust-free Clean Lab.
So this is a transparent conductive layer that could be part of the top cell in a tandem structure. It needs to be transparent to let some of the light through to the bottom cell.
The new layer of solar cells will be placed on top of a standard solar cell.
So here we have one of the solar cells aiming at making use of the blue light more effectively. So we'll measure it. So here we see the result, and it looks good because for the region of blue light, the curve is high, and that's what we were aiming for.
The top cell succeeds in capturing blue light. Now it's fast forward for solar cell research, and Charlotte is sure that the next generation of solar cells will be an important part of our future.
So we need to get away from fossil fuels, and solar cells is an excellent way of using the solar energy that's coming to Earth. And we need to use that much more than we do today.
But one problem with solar energy lies in how to store it. Electricity is generated during daylight hours, but it's needed for heat and electricity throughout the day and night. The batteries available today simply aren't good enough. But maybe the solution will be found here in Gothenburg.
So we should use this syringe pump to pump through everything.
Yeah. So I will hold for you here, and then you can take up with the...
At Chalmers University of Technology, scientists are in the process of testing a new, specially designed molecule, capable of both absorbing as well as storing the energy from the sun.
So my dream is that our molecules can be used for heating applications all over the world, so that we can provide heating in a future society where fossil fuels are not the desired option for heating applications.
With solar cells, the sun's energy is converted into electricity. But instead of doing this, Kasper Moth Poulsen wants to transform the sun's rays into chemical energy, achieving this with his own energy-smart molecules.
So we're trying to design a molecule that can absorb the sunlight and store the energy of the sun for certain periods of time, so that we can release it as heat when we need the heat.
Kasper's team are constantly testing new variants of the molecule. They are made up from common elements like carbon, hydrogen, and nitrogen. But in specific combinations, the molecules display unique properties. When Kasper's molecules are exposed to light, they transform. The atoms in them change the way in which they bind to each other. It is in this way that the molecules now can store more energy. If the scientists then add a substance that resets the old bonds, that's right, the stored energy is released.
That could be heating a house, industrial processes where heat is needed. Then we can create an energy system where we only use sunlight and our molecules.
Kasper's team has managed to create a new variant of the molecule. Now it's time to measure its properties.
So here we are exposing our molecule to a monochromatic blue light from a light-emitting diode.
The molecule is exposed to monochromatic light, a single color of light, to be able to track the amount of energy it manages to store. This time, the results are worse than Kasper had hoped. The molecule only captures 1/3 of the light's energy.
So this molecule is sort of okay, but it was not as good as we hoped for in this specific function.
However, the molecule is still fully charged with the energy from the light.
All right.
Now comes the next crucial test.
So here we have the molecule that we just made.
How much of the energy can be released?
Okay, so we're gonna put the catalyst here.
In order to make the molecule let off its heat, Kasper's team has developed an activating agent, a catalyst.
So this is a catalyst we use to trigger the heat release of our molecules. And then we're going to close up the chamber now.
Yeah.
They test the molecule inside a specially built vacuum chamber. The goal is to achieve as large a temperature increase as possible. So far, they have succeeded with around 50 degrees. But research is going very well, and they are constantly making progress.
So this is a heat release that we get from this experiment. We just get a 63 degree release.
Wow, this is much better than I had hoped for. Yeah. So here you have this nothing, no temperature gradient. But
yes.
then here a molecule hits the catalyst. Mm-hmm. The temperature goes up, and then it goes all the way up to more than 60 degrees. That is really amazing. Much to our surprise, we have seen quite some progress during recent years, and we are actually very optimistic about how we will be able to develop this system in the future. This is quite amazing because this is a world record temperature gradient in such systems.
It's not every day that Casper and his team set a world record, but for their energy-storing molecules, it's going quite well. Their hope is that they will be one of the solutions for our growing need of renewable energy. There are other research pathways as well, taking on the hunt for more environmentally friendly energy. How about learning from nature and making fuel from water?
Is it connected?
Can't see anything yet.
No, it should work.
In a laboratory at Umeå University, scientists are experimenting with the splitting of water.
We added the electrolyte and now we connect the solar cell. And then we should hopefully soon see water splitting when we switch on the light.
By copying how plants make their fuel, Johannes Messinger wants to form hydrogen with the help of only sun and water. Hydrogen is a fuel suitable both for cars and aircraft, and the exhaust gases are only consisting of water.
So if everything goes well, this will become a major part of the future energy system, and it will help us to store a lot of solar energy in fuels, and will help us to avoid carbon emissions and make the climate of the world better.
Johannes Messinger takes his inspiration from nature. His team is working to create an artificial leaf, creating artificial photosynthesis. In photosynthesis, plants use the sun's energy to convert water and carbon dioxide to oxygen and energy-rich carbohydrates. Johannes wants to do the same thing, but skip the carbon dioxide and allow the sun to transform only the water into oxygen and energy-rich hydrogen. This work starts here, through studying how the plants absorb light energy.
So the first step is to understand how photosynthesis works. And for this, we use this instrument.
Johannes charges the instrument with plant parts. Short flashes of light then start the photosynthesis in intervals.
Over here on the monitor, you can see the result, and you can see how much oxygen comes out on each flash that we gave.
The production of oxygen is an important piece of the puzzle in order to create photosynthesis. But the sun's energy alone is not enough. Plants also need a substance to kickstart the chemical process. That substance is called the catalyst. For this, plants use calcium, manganese, and iron, metals they harvest from the soil. Now Johannes' team is trying to get the perfect catalyst for their artificial photosynthesis.
Hey Thomas.
Hi Johannes.
Are you ready to show us something?
Yeah, I can show. We have the sample here.
Johannes Messinger is working together with nanophysicist Thomas Wallenberg, using an electron microscope to study their new catalyst in detail.
So let's look at this catalyst here. You see this wrinkled structure, that's a catalyst, supported on the carbon nanotubes.
They build a basic structure out of carbon, to which they can then attach different combinations of metals to act as catalysts. Once the artificial catalyst is made, it's hooked up to an organic solar cell they themselves developed in the lab.
Hi, Christian and Jonas.
Hello.
Can you show me your latest solar cell you got?
Yeah, we have one here.
Together, the parts form the artificial leaf which will transform water into fuel. If it works now.
When we switch on the light, we hope that now we will see bubble formation here at the electrodes. On one side, there should be oxygen bubbles, and on the other side, there should be hydrogen bubbles. So maybe let's start. Okay. Can't see anything yet. Oh yeah, I can see the bubbles coming. So there is hydrogen on this side and oxygen on that side. Very good. Excellent.
The artificial leaf works, successfully transforming ordinary water into fuel.
Well, what we have shown with this device is that we can actually convert the solar light into a chemical fuel, that we can imitate nature and be even more efficient in producing fuels than nature.
Energy research often focuses on harvesting energy from the sun, that huge power source far out in space. But considerably closer to us, on a much smaller scale, there is another untapped resource. Here, Per Eklund is trying to create a unique material, but he has a very tricky problem to solve.
I want to make materials that, on the one hand, are good electrical conductors, but at the same time conduct heat poorly.
This maybe sounds like a simple task, but it is complicated, and it's called thermoelectricity. And if Per Eklund's team succeeds, well, we could all be taking part in generating electricity.
So anyone who's had a laptop on their lap knows that it gets warm after a while. So thermoelectricity means that we develop materials that can harvest that heat, or heat difference rather, and turn it into useful electricity.
Per Eklund and his research team are here at Linköping University. Their work on the new thermoelectric material begins with mathematics.
Okay, but that sounds good. Then it would be like a bit over 12 millivolt in output voltage, so...
They are calculating out a material that needs to have two completely contradictory properties. When one side of a material is heated, electrons start to move from the hot to the cold side. And as they do, an electric current is generated. In order for it to work, the material has to be a good electrical conductor. The problem is, at the same time, that material is also good at conducting heat. The two properties are connected. And when the heat quickly dissipates, the temperature difference disappears and the current ceases.
Yes, it is a really difficult problem, but that's why it's so interesting. It really is a big scientific challenge. Well, we want to decouple the mechanisms for electrical and thermal conduction so that we can optimize these properties independently of each other.
To succeed with this, Per's team has to create a whole new kind of material. In a vacuum chamber, the scientists mix extremely small structures of the metals they want to try.
So we're making a ceramic material based on calcium and manganese. So these materials have unusually good properties for converting heat to electricity, but you really need to get the elements in the right proportions.
The scientists irradiate the metals so strongly that small nanoparticles dissolve and attach to a thin film, atomic layer by atomic layer. Per brings the new material to the measurement station to look at its thermal properties.
Okay, here, got it. Let's test the material.
Sure, let's try this.
The material is first introduced to a difference in heat.
Gonna apply the heat now on one side.
Is it now going to generate enough voltage? They're looking for a measurement of up to 20 millivolts.
Yeah, nice.
Got it.
Yeah, and a pretty high output voltage too. That's really good.
Great.
Great.
Quite high actually.
The result is unexpectedly good.
Well, we already have a good material. So what remains to be done now is to make devices in sufficiently large numbers and sizes and at a decent cost.
Per Eklund's team continues developing their thermoelectric materials. Hopefully, these materials will be one of the solutions that in the future can provide humanity with environmentally friendly energy. And at Swedish universities all across the country, researchers are continuing the search for future energy solutions. It may be about solar cells, molecules, or photosynthesis. But it's ultimately about the future of our planet.